Hello, everyone. I will talk today about compartmental dynamical systems and how do we use them to understand the global carbon cycle. And for this talk, I will deal with two questions. One is how to generalize the structure of carbon cycle models. And the other question is can we learn something about the qualitative behavior of general classes of models? And for this, I will use this concept of compartmental systems. This is a concept from dynamical systems from mathematics, which is a very useful concept to generalize really large classes of models. And this concept can actually generalize any system that has to do with mass balance. So let's think about compartments that store mass. In our case, we're interested in compartments that store carbon. These compartments will have inputs coming from the external environment, and they also release carbon to the external environments. But at the same time, these compartments may or may not exchange mass with other compartments. In an ecosystem, obviously, there are exchanges of carbon between vegetation and soil, or within parts of the vegetation. So therefore, we will have exchanges of mass. So we're going to focus on any compartment within our system that stores mass, receives mass from the external environment, releases the mass to the external environments, sends or transfers mass to any compartment J, and receives mass from any compartment J within our system. All of these fluxes are actually non-negative because they are masses, so they can never be negative masses. So therefore, one important mathematical property of the systems is that they are non-negative. So for each compartment, we can actually do a mass balance to look at how the mass of the system changes over time, or the mass of the compartment. And that mass balance will be equals of what is coming in minus what is being released from or to the external environment, and also the inputs and output fluxes among the different reservoirs or the different compartments that are within the system. Again, these quantities are all non-negative, and this is an important property. Now, the fluxes of the transfers of carbon among compartments are usually smooth fluxes. You don't have really large jumps. There's usually smooth transitions in these fluxes. And if this is true, then we can write the fluxes in terms of the mass of carbon that we have stored in our compartments. And this is due to this property of differentiability, because the fluxes are differentiable functions. Therefore, we can write them in terms of the mass that we have stored in the compartments. So if this is true, then our differential equation for the change of mass in the compartments, we can write them in terms of the mass of carbon that we have stored in the compartment for the output fluxes. Input fluxes from other compartments are also going to be expressed in terms of the mass that is stored in those other compartments. And independently, we have the inputs coming from the external environment. We can make an additional simplification of these equations. And if we express, or if we define the loss of each compartment as the loss going to the external environment plus the losses that go to other compartments, then we can write the differential equation for each single compartment in a much simpler form. And if we can do that for all of the compartments, then we can write a whole system of differential equations in vector and matrix form. Here, we have the change of mass of the compartments over time being expressed as the inputs of mass coming from the external environment times a matrix that has all the losses to the external environment and all the transfers to other compartments, depending on the mass of carbon being stored in those compartments. when we can write a system of equations in this way, we have something called a compartmental or reservoir system. And something very important about these systems is that the matrix B has three very important properties. One is that the diagonal elements are all non-positive. The off-diagonal elements are all non-negative. And the sum of the columns of our matrix B give us the release flux, the release coefficients to the external environment. If all those release coefficients are negative, then we have that B is actually a strictly diagonally dominant matrix. And that means that you can always find the inverse of this matrix, which is an extremely important mathematical property of our compartmental system. And we can write many models of the carbon cycle in this form. This is an example of a model that has a vegetation compartment and a soil compartment. Through photosynthesis, carbon is incorporated into vegetation. And through autotrophic respiration, we have CO2 release. And through leader transfers, carbon will go from vegetation to soils, and from soil, we will have heterotrophic respiration. We can take this simple carbon cycle model, and we can write it in matrix form, looking at the change of mass of carbon in the vegetation compartment, in the soil compartment, as the result of the inputs of photosynthesis that go into the vegetation compartment. From the vegetation, we have losses, and a proportion of those losses will go into the soil compartment, a proportion alpha. And from the soil compartment, we will have losses that are expressed as heterotrophic respiration. So we can easily write models of this form. In case we will have non-linearities, for example, in case we will have a photosynthesis depending on how much vegetation carbon and how much soil carbon you have stored in the system, you can also express these non-linearities using this matrix and vector form. So, do carbon cycle models in general meet the definition of compartmental systems? Well, the answer is yes, as long as the carbon cycle model meets the mass balance requirement. You can always write a carbon cycle model in this compartmental form. And in my research, I usually write these compartmental systems in this form with a little bit more detail, saying that the changes of the mass in the compartments over time are the result of the inputs from the external environment coming into the system. And those inputs may depend on time, and they also may depend on the mass that is stored in the compartments at that particular time. And the same thing for our compartmental matrix. The compartmental matrix may depend on time, and it also may depend on the mass of carbon stored in the system at that particular time. And if we know the initial conditions, if we know how much mass we have stored at time zero, then therefore we will be able to find a solution of this system of equations. So again, our vector of inputs will be a vector value function of external inputs coming into the system. And our compartmental matrix is a matrix value function of process and transfer rates. They tell us how fast carbon cycles inside the ecosystem. In this course, you have been studying the matrix approach developed by Dr. Luo. Usually this matrix approach can be written in this form, which you probably can see that is a very, very similar in the form of the compartmental systems that I'm showing you in this talk. The vector of allocation coefficients times the photosynthesis term, you can do this multiplication and you will end up with a vector. And this vector will be the inputs in our system in this compartmental case. If you multiply these matrices, you can define the resulting matrix as the matrix B, and therefore you will obtain this general matrix representation. So in other words, the matrix approach you are studying in this course is a particular case of the more general compartmental representation that I'm presenting in this presentation. We can use this general expression to classify different types of models. And we use this representation to classify models according to dependence of time and dependence on the contents of the reservoirs. For example, if we have models in which all the input rates and the cycling rates in the system are constant values with no dependencies on time and no dependencies on the vector of states, then we have what we call a linear autonomous dynamical system. If the inputs, photosynthesis, and rates, decomposition, will change over time, then, but not depending on the states, then we have a linear non-autonomous system. And there is a very important difference here, because as opposed to the autonomous system where all the rates are constant, here these rates will change in any particular form. When we have systems in which there are nonlinear interactions among the contents of the reservoirs, when the inputs depend on how much carbon you have stored within the system, or when the rates depend on how much carbon you have stored in the system, then we have a nonlinear autonomous system. And if in addition to that, we have time dependencies, then we have a system that we call nonlinear non-autonomous dynamical system. This later case is the most complex case that we can have. It's a very difficult type of system to study. Many different behaviors can be obtained. And the most simple system is the linear autonomous dynamical system. To be able to understand dynamics in general, it's actually very useful to understand first linear autonomous dynamical systems before moving and study the non-autonomous and the nonlinear dynamical systems. And actually, this linear autonomous dynamical system has actually an analytical solution when you have all the input fluxes and the rates constant. And if you know the initial conditions, the solution over time will be given by this expression. It tells you how the initial mass will decompose over time according to this matrix exponential, and how the new inputs will get processed also according to this matrix exponential. Over time, this type of system will converge to the steady state. And the steady state solution of this system can be expressed as this. It only depends on the input vector in our compartmental matrix. It doesn't depend on the initial amount of carbon that you have at T0. So therefore, the system will converge always to the same steady state, independent on the initial conditions. This is a very important property of these linear autonomous systems. In the literature for dynamical systems, you might have seen this type of diagrams before that tells you about general classes of behaviors that you could expect for dynamical systems, systems that rotate along some trajectories, some systems that converge to a particular point in a very smooth way, or in some cases through oscillations. And there are systems that are unstable, that they explode or diverge from a particular point. And turns out that our linear autonomous dynamical systems only have these two possibilities. They can only be a stable node or a stable spiral. And the reason for this is because this compartmental matrix, the mathematical properties of the compartmental matrix, can only lead you to these two different cases. It also means that mass can never explode. You can never get mass that is created and the system will explode in terms of mass. You can only get very well-behaved systems when you have these linear autonomous dynamical systems. And they either converge to the steady state in a very particular smooth form, or they can oscillate around that steady state and reach that steady state eventually. So, and it's very important that we do not mix these concepts between the autonomous systems and the non-autonomous systems. Again, when we have a linear autonomous systems, depending on independent on the initial conditions, the system will always reach that or tend to reach that steady state over time. And if you think about it in terms of the phase plane of one compartment, the mass of one compartment versus the mass of another compartment, you reach a point in that phase plane. The trajectories will go towards that particular point. But when we are in a non-autonomous linear system, everything is changing over time, and the trajectories will never reach a point. If we look at the phase plane, we plot the mass of one compartment versus the mass of another compartment, we will see that we will have trajectories and never will approach a particular point. What we could potentially have is that trajectories will get closer and closer to each other. But this is different than approaching a steady state. In other words, a non-autonomous dynamical system will never reach this concept of a steady state because by definition, they shouldn't converge to one point because things are not constant in the non-autonomous dynamical system. Having this matrix representation is very useful to study properties of our carbon cycle models. Professor Lu has shown you the concepts of carbon storage potential and carbon storage capacity. We can also obtain those terms with our matrix representation by solving this equation for X, and we will have the carbon storage potential and the carbon storage capacity. And I think you probably will learn more about this during this course. I just wanted to show you here that you can also obtain those concepts in this matrix representation. But you can do a lot more with this compartmental system representation. For example, you can obtain diagnostic times. These are metrics that inform you about the time the mass stays in a compartment within a system, or the time that it takes for the mass to go through the entire system. And these are the concepts of ages and transit times. And I will talk about these concepts in a separate video. In addition to that, we can study other concepts. So for example, the information content of a system using concepts of entropy for dynamical systems, or we can use concepts from graph theory to study the connectivity of our dynamical system. So in summary, carbon cycle models can be generalized as compartmental dynamical systems, and this is due to the principle of mass balance because it poses a very strong constraints on the overall dynamics of the carbon cycle models. And this is due to the fact that mass balance poses a very strong constraint on the compartmental matrix. The matrix equation of land carbon models is also a compartmental dynamical systems. And once we have this compartmental approach, we can study other important diagnostics such as ages, transit times, entropies, connectivity, and probably many other more. Thank you for your attention.